Chapter number 10, Vector Algebra. We already studied vectors in 11th standard. Now here we have some further concepts of vectors. So even you might have used in physics also. Vector is nothing but a quantity which has both magnitude as well as what? Direction. In general it is defined as what? Vector. A quantity which has magnitude as well as direction. Magnitude and direction is known as a vector. Right? Now the general way of defining vector is this. If you remember, members of R2, that is Cartesian plane, and R3, as far as your syllabus is concerned, these members of R2 and R3 are called vectors. These are called what? Vectors. Members of R2 or R3. So if you pick up any vector which has two components, then it is called vectors. In R2 are called plane vectors sometimes. Plane vectors. And vectors in R3 are called sometimes space vectors. Right. So every member of R2 and R3 will have magnitude as well as direction both. Right. Or another way of defining the same thing is here, vector is a directed line segment. Remember, a directed that has a direction, a directed line segment. Remember, directed line segment which has a direction. Okay, if I take one line segment like this here, for example, and I give the direction like this, it starts from here and suppose it ends here. So this is read as vector AB. How do we read? Vector AB, and we give the direction like this. If I take the whole as small a, then this is also read as vector A, remember. Vector A. How do we read? Vector A. Suppose if I have one more directed line segment like this, if I have one more line segment like this, this is A, this is B. Suppose I'll call this as B, for example, vector B. So here vector starts from B and ends over here. So this is read as vector BA. Or you can also write vector B here, remember, like this. So directed line segment is nothing but a vector. So it has some specific direction, remember. Okay, now here we first mention one more terminology that's called here initial point, from where this vector starts. So this is called initial point sometimes. Initial point. And vector ends here, so this is called terminal point here. Terminal point. Terminal point, initial point. For this become here initial point and this become terminal point, remember. Initial point means what? The word itself says from where the vector starts, that's the initial points. Vector ends here, so that's a terminal point. This is initial point, here this is terminal point, remember. Fine. Now over here we define one more concept of position vector. So let me write that first. Position vector. Okay, so here, as I told you earlier, vector is a point in R2 as well as R3. So if I consider, for example, only R2 like this, you know x-axis, y-axis, O which is origin, in R2 it has two components. Suppose I have point P here, position vector, let me take x comma y which are coordinates. If I join like this here, let me join like this. So this is nothing but the what? Vector OP. Right. It starts from origin, remember, and which is equals to x comma y. So this is nothing but the position vector of the given vector. Position vector of the given vector. Position vector of vector OP, remember. Indirectly it is this minus this, remember. Okay. If I have in general, for example, if I consider let's take one point P here whose components are, let me write for example x1, y1, z1. In R3 I'm talking, and Q be this x2, y2, z2 here, and so this is P, this is Q here, remember, this is vector PQ, this is read as vector PQ. Now what's the position vector of this? That is in general this minus this, so it will be x2 minus x1 comma y2 minus y1 comma what we can write here, next one is z2 minus z1. So this is defined as position vector of this position vector in general. Right. What's the position vector? Coordinates representing given vector. Okay, it is just coordinates representing the given vector. And now once you have the coordinates, so here let me call this as vector A, for example. If I write here vector A, then position vector or the coordinates of A are this. Here coordinates are this. Let me call this as some vector small p, for example. So small p equals to vector PQ, remember. That is this one. This way it is defined. Okay. Now the next point is how to write the magnitude. That's the next point. So here the magnitude of this let me write vector A here, that is denoted by this symbol. This is read as magnitude of A, vector A, remember, which I can write like this also, magnitude of OP so as I mentioned here, magnitude in this case, if this is vector say OP or vector A, so OP or you can say vector A with position vector, let me take xy here, you know position vector here 0, then the magnitude of this vector, that's also called the length of the vector, which is just the distance of terminal point from this initial point. So you can write root of x minus 0 the whole square, which is x square plus y square. Here remember position vector is nothing but what? X comma y. So this is the definition of magnitude or length of a vector. Length of a vector, remember. Fine. If you have vector in R3, for example, that is if you consider a vector with position vector like this, so if vector OP, let's say vector A with x, y and z here, this as a position vector, then the length of the vector A, which is equals to length of the vector OP, which is given by root of x square plus y square plus z square. Same way, just here you have three components. This is the definition of magnitude of a vector, remember. Now about directions of the vectors. About directions of vectors, we define in this way. If I have two vectors, vector A here, let's see, another vector B, these two vectors are in the same direction, then one vector must be positive multiple of the other one, where k is here positive. If two vectors are in the same direction, remember. If two vectors are in the same direction, then one must be positive multiple of the other one. We'll discuss later on with some examples. Vector A, vector B, they are in the same direction, then one must be positive multiple of the other one, where k can be any number or scalar in general. Now, if I have vectors like this, here, vectors are in opposite direction. Suppose one vector A like this and the other vector B like this. The vectors are in opposite direction here. So in that case, vector A equals to k times vector B, where k is negative, remember. K is negative. So here vectors are in opposite directions. Right? Here vectors are in opposite direction. In the previous case, vectors were in same direction, opposite directions, remember. In the previous case, were vectors in the same direction. Here, vector A and vector B are in same directions. Same direction if positive multiples. Negative multiple, opposite direction, remember. And if like this, if I have one vector is like this and the other vector may be like this, so we say that they are in different directions. Different directions, remember. Different directions. So in this case, vectors are not multiples. This is not a multiple of this. For any k, remember, for any k belongs to R. Right? If they are not multiples, we say that they are in different directions. Now, here we discussed 2-3 standard types of the vectors. One is zero vector, that is also called null vector. One is zero vector, zero or null vector. Zero vector or null vector, that is a vector where initial and terminal are same. Initial point is same as terminal point. Terminal point. Such a vector is known as which vector? Zero vector. That is, if you take in R2, then position vectors would be 0, 0. If you take in R3, then it is 0, 0, 0. These are the null vectors in R2 and this is in R3, remember. Position vector will be always 0. Then next one will be unit vector. Unit vector. What's the unit vector? Vector having magnitude equals to 1 unit. Vector, let's say A is called unit, if its magnitude, if its length is 1 unit, remember. 1 unit. Any vector with magnitude equals to 1, it's known as unit vector. We'll see later on with some more examples. Okay. Third one, that is collinear vectors. Let me write collinear vectors. Collinear vectors. So when two vectors are said to be collinears, if vectors, let me write vectors are called collinear, if they are parallel to same line. If they are parallel to same line. if they are parallel to same line, right? What's the meaning of this? Either they are positive multiple or negative multiple. Such vectors are said to be collinear vectors. Remember, here magnitude and directions are not important, so let me write irrespective of direction and magnitude. Directions or magnitude, remember. Such vectors are said to be, which vectors? Here, collinear vectors. Okay. Then equal vectors. Here, next is fourth one, that is equal vectors. So two vectors are said to be equal if their magnitude and directions are equal. Vectors A and B are called equal if their magnitude should be equal, and second thing, their directions must be equal. Remember, their magnitude and direction should be equal. Directions are equal. Then such vectors are said to be equal vectors, and we write in this case like this: vector A equals to vector B. If I have one vector like this in this direction with magnitude equals to, let's take 2. I have one more vector of the same length, vector B, in the same direction. You can see magnitude of this one is also 2. These two vectors. So here their magnitude and directions are equal. So we say that the vector A equals to vector B. This is one simple example. Fine. And then here, sometimes we have additive inverse of a vector. That's sometimes called negative of the given vectors. So let me write that: negative of a vector. Negative of a vector. That is, additive inverse in general. So if you have one vector A, for example, vector A to B, like this. This is A, here B. This is B, right? Then if I consider vector from B to A, like this, here, now from B to A. So this is nothing but the negative, that is minus of this. Fine. So here, therefore, you can write vector AB equals to minus, this is nothing but which vector? BA. These two are same, remember. Okay. So that's nothing but here negative of a given vector. This is vector AB. Now here this is minus vector A, that's from B to A, remember. So minus B to A, these two are equal in this case. Fine. Now I have already told you that vectors are nothing but points in R2 and R3. So here this properties comes from the concept of R2 and R3. So these are some properties which are quite obvious properties for vectors, which would always hold true, remember, for any vectors. So for any vectors A, B and C, let's write for 3 vectors. The first one, that's commutative property. This is always same as this, remember, this is always true. Second one, associative property. For 3 vectors, this is always true, remember. You know such things, just for your information I'm noting this. One more, that is vector A plus null vector equals to null vector plus vector A equals to always given vector. This is again true. Then next one, that's that additive inverse property. What's additive inverse property? That is, if I have a vector, if I take its negative, that's minus of this vector A, if I add this 2, if I do reverse negative of a vector plus the given vector, then the answer will be always a null vector. Right? This is always true, remember. This is sometimes called what? Additive identity, remember. Zero vector, that's additive identity, which is always true. Fine. Now next, I want to write the standard unit vectors in R2 and R3. Unit vector means magnitude equals to 1. If I consider here like 1, 0 in R2, then you can verify its magnitude will be here. Length of this, magnitude of this vector will be root of 1 square plus 0 square, which is 1 here. That means this is unit vector. So this is sometimes denoted by I cap. And similarly j cap, you know it is 0, 1. These are the standard unit vectors in R2. Unit vectors in R2. We know this. Same way, if I take I cap, which is 1, 0, 0 in R3, j cap, you know 0, 1, 0, and k cap, you know it is 0, 0, 1. These are nothing but standard unit vectors where in R3 magnitude of each of this here equals to 1. Magnitude of each of this one equals to 1. That you can verify very easily. Length of this is 1, this is 1, and so on. So here if I try to show it, these are the 3 coordinate axes, x, y, and z. This is origin, so I cap is in this direction. This is I cap. J cap is here in this direction, and this is in the direction of k cap, remember. So here the components will be 1, 0, 0. Here components will be 0, 1, 0, and here components will be 0, 0, 1. Right? This is 1 unit, this is 1 unit, this is 1 unit. This is null vector, you know. So these are the standard unit vectors where in R3. Now with this concept here, if I have any vector in general, if I have vector A with like position vectors equals to x comma y, then this we can write x I cap plus y j cap in R2, remember. Okay, and same way if I have in R3 like vector A equals to, suppose I have x y z here. So in R3 I can write x I cap plus y j cap plus z k cap. Right. We have this as well as this. This is another way of writing the same vector. Here it is in form of coordinates. This is in form of ij, remember, and this is in form of coordinates. This is in form of ijk. So here sometimes x, y, z are called scalar components. Are called scalar components of the vector, remember. These are called which components? Scalar components of a given vector. And if I write with xi, yj, and zk, if I write this, these are called vector components. These are known as which components? Vector components, when it is expressed with ijk notation. If it is just in form of scalar x, y, and z, then these are called the scalar components. Scalar components, vector components, when they are in ijk notation. Okay, so now even as we did again, 2 times we did, one more time I'm showing. If I take vector A equals to, for example, x I cap plus y j cap plus z k cap, then its magnitude, the length of this vector will be this, x square plus y square plus z square. This is the length of a vector, right? If I have one more vector, vector b equals to, suppose I have I cap plus 2j cap plus, let me write 3 cap, 3k cap, then what's the length of this vector b? It will be root of 1 square plus 4, 2 square plus 3 square, which is 9. So this is nothing but root 14. You can keep in this form only. If I take one more here, let me take this vector c equals to, I'm taking one more vector here, I cap minus j cap in R2 only. So then what's the length of this vector? Which would be root of here 1 square plus minus 1 square, which is nothing but the root 2. That's the length of this vector c. Fourth one, let's write one more vector, vector d equals to 3i cap plus 4j. Let me write this. So length of the vector d equals to here root of 9 plus here 4 square, which is 16. So length equals to 16 plus 9, 25. So length will be 5. Okay. So here is a result based on unit vector. So that says that if this is a non-null vector, then vector upon its magnitude is, this is nothing but is unit vector is a unit vector in the direction of a given vector, in the direction of the given vector, direction of the vector A here. This is always true. Vector upon its magnitude, it would be always a unit vector. Vector upon its magnitude is always a unit vector, remember. Means its length is 1. So if this is a vector, vector A, the magnitude of this vector can be anything, but if I find this vector, this upon its magnitude, this is also vector, then this is a new vector which is in the direction of the given vector. The direction of this vector which I've shown here, it is same as this. These two are in the same direction, but if you get the magnitude of this, it would be just 1, remember, and therefore this is a unit vector. Always true. Vector upon its magnitude is a unit vector in the direction of the given vector. So like this here, if I take an example, one vector, suppose I'm taking this 1 into I, that is, let me write I minus 2j plus 3k. You can write cap here, right? What's the question? The question is this here. This is a question. We find unit vector. This is a question. Find unit vector in the direction of given vector. In the direction of the vector, direction of the vector A, remember. Okay, so what we do? The required vector is this. You have the prepared formula. What's the required vector? That is vector upon its magnitude. This is the unit vector in the direction of the given vector. Now what is this? This is nothing but I cap minus 2j cap plus k cap, 3k cap upon its magnitude. What is its magnitude? 1, 4 and 9. 1 plus 4 plus 9, which is root 14. So you have 1 by root 14 I cap minus 2 by 14 j cap plus 3 by root 14 k cap. This is a new vector. there's a new vector which is in the direction of the given vector, and it will be unit. If you get the magnitude of this, you will see that it will be unit vector, remember. Fine, this is always true. I have chosen one vector in R3, sorry, you can take one vector like this also. If I take one more example here, vector B equals to, let me write 3i cap minus 4j. In R2 I have chosen. Where? In R2. Okay, what is its magnitude? Let's get the magnitude here. What's the magnitude? That is 9 plus 16, which is 5. That's not 1, so it's not a unit vector, remember. So how do I make the unit? So required unit vector, that is vector upon its magnitude. What is its magnitude? That's 5. So you will get the 3 by 5 I cap minus 4 by 5 j cap. This is the required vector. Right. Required unit vector, remember. The important one is required unit vector. Fine. Now with this concept we define here 3 things. Let me see that here now. So now we write direction, cosines, angles and ratios of a vector. So here we start with a non-null vector. Let's take, I'm taking one vector R which is not a null vector, remember, which is not a null vector. Okay, so here I'll consider 3 coordinate axes. Let's consider 3 coordinate axes here. Okay, so we are doing in R3, remember. So let me call this as the x-axis. This is your null vector. This is y-axis, and this is z-axis. We have chosen one point P here. There is one point P here. We are joining with origin, so this becomes vector R, remember. So here OP, which is nothing but a vector R. Okay, let me take the coordinates or the position vector of this equals to here x, y, z. So therefore you can say vector R equals to vector OP equals to, what's the position vector? X, y, z. In short, vector R is this: x I cap, y j cap plus z k cap. Okay. Now here we consider angles made by these vectors with these 3 directions. So I'll call this angle as alpha here, this angle as beta here, and this angle as gamma here. So what is this alpha? Alpha is the angle between the x-axis and the vector OP. What is beta here? That is angle with here y-axis and vector, and gamma is this angle with z-axis and the vector. Then here it can be shown, we'll see it later on, cos alpha will be the first component upon the magnitude of this vector. That is, I'll write small r. Let's take magnitude of this vector. Magnitude of this vector equals to small r. Cosine beta, will derive this later on, I'll tell you. Second component upon its magnitude. And cosine gamma, that is equals to third component upon its magnitude. So here cos alpha is x by r, cos beta is y by r, and cos gamma is z by r. So if you just observe this here, x, y, z upon its magnitude. So these are nothing but the components of the unit vectors. So here cos alpha, cos beta and cosine gamma, these are called, the word itself says direction cosines, remember. These are called what? Direction cosines. These are called direction cosines. What are the direction cosines? Vector upon its magnitude, nothing more than that. It's indirectly unit vector, remember. X, Y, Z upon its magnitude. So here this cos alpha, cos beta and cosine gamma are called what? Direction cosines, remember. This simply unit vectors. And if you get alpha, beta and gamma from this, these are called direction angles. So if I write alpha here, you know now alpha can be written as cos inverse x by r. Beta can be written as cos inverse y by r. And gamma can be written as cos inverse z by r. So here this alpha, beta and gamma, these are called direction angles, remember. Direction angles, remember. These are called direction angles. Alpha, beta and gamma. Cos alpha, cos beta and cosine gamma are called what? Direction ratios, remember. Direction cosines. Cos alpha, cos beta and cosine gamma are called direction cosines, whereas this alpha, beta and gamma are called what? Direction angles. Sometimes this cos alpha is denoted by small l, cos beta is denoted by m here, and cosine gamma is denoted by small n here, right? L, m and n. So these are three nothing but direction cosines, as I told you. These are nothing but what? Direction cosines. So here from this, if you just rewrite three components, that is here x, y, z, this can be expressed in form of if you go back to formula, it will be LR. This is nothing but the MR, and here this is nothing but next component is NR, remember. This would be always multiple of position vector of this. So these are called direction ratios. Direction ratios, remember. These are called what? Direction ratios. Multiples of what? These are nothing but what? Multiples of position vector of this vector. Given vector has this position vector. These are simply multiples. So these are called direction ratios. LR, MR and NR. Right? These are always, in the proportion of the given direction cosine. So these are called sometimes direction ratios. Cos alpha, cos beta and cosine gamma, LMN are called what? Direction cosines. Alpha, beta and gamma are called direction angles. Direction angles, direction cosines and direction ratios. Now we note that here, we must note this. If I write L squared, if I write plus M squared, if I write plus N squared, then this must be what? It has to be 1, remember. That is what I'm trying to tell you is cos square alpha plus cos square beta plus cos square gamma, that is here cos square gamma is always 1, remember. What is alpha, beta and gamma? Direction angles. What is LMN? These are nothing but direction ratios, remember. Right? Why this is 1? Because this L, M and N, if you just go back to definition of L, M and N, this is simply unit vector. So magnitude has to be 1, remember. If I take a simple example, you will realize L, M and N, if you just go back to definition of L, M and N, this is x by r here. What is this? This is y by r. And what is this? This is z by r, So if I square this and if I add them, then it is x square plus y square plus z square. This is just for your information I'm writing. X square plus y square plus z square upon what? R square. And what is this? This is nothing but magnitude square. how we wrote the magnitude square, r square upon r square, so that gives us 1. In short, this L, M and N is a unit vector, that's why we have this, and therefore magnitude has to be 1, and therefore we have this, remember. Okay, so let me take one simple example of this 3, you will realize here. So if this is a vector I cap plus j cap minus 2 cap, I want to get direction cosines. So what will be direction cosines? That is, you know here L, M and N. These are the direction cosines. What is L? That is first component upon its magnitude. What is the magnitude of this vector here? That's a root of 1 plus 1 plus 4 here, which is root 6. Right? So you will be having 1 by root 6. What is M? Second component upon root 6. And what is N here? That is third component upon root 6, remember. X upon R, Y upon R and Z upon R. So direction cosines will be this 1 by root 6, 1 by root 6 minus 2 by root 6. You can verify if you write L square plus M square plus N square, it will be exactly 1. And here 1, 2 minus 2, these are nothing but what? Direction ratios. Right. So direction ratios, if you write, ratios will be, direction ratios will be just 1, 1, minus 2. These are the direction ratios here, remember. So now let's see some riddles. The first one is here, triangle law for vector addition. Right, vector addition. I'm sure you must be knowing. You might have used even in physics also. So in a triangle, if I have one vector here, let's say vector AB. This is another vector. Let me call the vector BC. If I add these two, that's nothing but a vector here AC. So in a triangle, vector AB plus vector BC, that's always equals to vector AC. AB plus BC is always equals to AC. This is known as, triangle law, remember. This is always true, right, in a triangle. One more, that's about parallelogram. If I have such a parallelogram, so next let me write parallelogram law for vector addition. So I'll take one parallelogram. In a parallelogram, opposite sides are equal, or you can say parallel. So this is, say, vector OA. I'll denote with vector A. Okay. One more side I'll take here. Let me take another side here. Okay, let me take over here, for example, vector B here. So this is vector B here. Then the opposite sides of the parallelogram will be this. This is opposite side and it is in the same direction. So this is again vector B. This is opposite side but the same direction. So this is also vector A. So if I join this vector A, vector B, then this become a diagonal, and which has to be the sum of these two, as I did here. You see, AC is the sum of two sides. So this is nothing but the vector A plus vector B. Right? So the sum of the two adjacent sides and a parallelogram always represent by what? Diagonals. So here diagonal in a parallelogram is equals to sum of what? Two sides. Sum of two sides, remember. That is, diagonals equals to, as you can see, vector A plus vector B. This is always true. If this is one side, there is another side, then the side, this diagonal of this parallelogram, it would be sum of the two sides, and this just comes from the triangle law, remember. Okay, now one more thing which we already studied in 11th standard. If you remember section or division formula. So we have the same formula here for vectors, remember. So let me write here section formula. The next point is, let me write section formula. We did the same thing in coordinate geometry in 11th standard, if you remember. What we are writing? Section formula. So we have here two vectors. Let's write like this here. So we have a line segment here. Let's say P with position vector. Let's write here A, vector A. Another point Q with position vector B. We have one point R whose position vector is vector R. Let's write like this. And here, let me write as we were doing, R divides line segment PQ. R divides line segment PQ in the ratio, say, M is to N. So this is nothing but M unit and this is nothing but N unit, if you remember. We did the same thing, if you recall. Then the position vector of this here, position vector of R, then this R is given by MB bar, vector B, if you remember, plus NA, opposite, if you remember, upon M plus N. In general, this is the formula. This will work for both internal as well as external division. This is useful for both external as well as internal division. External and internal division, remember. What do you mean by external division? That is, that point of division, this R is outside the line segment AB. What about internal division? That point P is inside the line segment AB. I'm not emphasizing much on this. You know, this is very well known formula from 11th standard, division or section formula. Opposite yaad rakhna hai. M with this, M is taken with this, and this N is taken with this into this plus this into this upon M plus N. Applicable to both external as well as internal division, remember. External division means what? Ratio is negative, and internal division means what? Ratio is positive. You know, here if you have M equals to N, then you will get the midpoint, remember, right? So here midpoint, so here you have point P, here you have point Q, and that R is exactly in the middle of this. So here M equals to N, remember. In this case we have what? M equals to N. Here position vector is vector A, here vector B, and suppose this is R. Midpoint, remember. So in this case the midpoint, which is vector R, that's given by the average of these two. M equals to N. So it will come out and here it becomes 2. So vector A plus vector B by 2. This is the formula. You know, this is also very well known expression. Average of the two components. Right? So position vector of the midpoint. Your R is the midpoint, remember. So these two are equal. So you will get M equals to N. Put M equals to N here, you will get exactly this. Average of the two components, that you know very well.